So let's consider a linear homogeneous constant coefficient system like this, x prime equals ax, where the coefficient matrix A is invertible. Okay, so with this criterion, if we look for equilibrium solutions, then an equilibrium solution is a point where x prime is equal to 0. But if x prime is equal to ax, then that implies that ax is equal to 0. But if A is invertible, then AX equals 0 implies that X has to equal 0, right? The only solution to the homogeneous equation for an invertible matrix is the trivial one. So in this case, the origin is the only equilibrium. Okay, and this is what we will look at. We will always look at this particular case. So let's see. So then also, since A is invertible, we know that 0 is not an eigenvalue of A. All right, so let's look at the possible cases for the eigenvalues of A. So we could have lambda 1 less than lambda 2 less than 0. So this is two distinct negative eigenvalues. Okay, so what does the situation look like in that case? Let's draw a phase portrait. Okay, so I'll take my, here's my x and y axes, and then suppose we've got an eigenvector that looks like this one here. So this will be our v1 corresponding to lambda 1. And then suppose we've got some eigenvector up here, and this will be our v2. Okay, then here's what's going to happen. Let me extend these lines a little bit here. Okay, and if we look at what's going to be on a, if we start on a particular axis, so say we start at this point right here, we're on the v1 axis, then the eigenvalue is negative, so we're going to move down toward the origin as time increases, right? So in other words, I'm looking at looking at this critter right here, e to the lambda t times v, and I know that A is going to make something that is on this eigenspace evolve in a way that keeps it on that eigenspace, because that's what eigenvectors do. And based on the fact that lambda is negative here, that means this is going to be a decaying exponential, so it's going to suck me in toward the origin. Okay. Similarly, if I start somewhere here on the v2 axis, I'm going to get sucked in this way. Now, I have that the lambda 1 is larger in magnitude out here, so this is lambda 1 in absolute value is bigger than lambda 2, which means that its behavior as an exponential is going to be dominating. So in other words, let's see what happens here. So we're going to have some large negative value and some small negative value. So here's e to the lambda 2t, and this other one is e to the lambda 1t. So for large values of t, for negative values of t, you're going to see this one is dominating. It's the big one. And so as a consequence, what you have is, let's draw some trajectories here. If I start at some point here, it's going to see the v1 eigenvector the most, and it's going to be moving this way until it gets too small and the other one starts to dominate, and then it'll come in like this. And so we'll have these curves that come in like this. And that's the same regardless of which side they come from. They're all going to be coming in to the origin, and so they'll start off looking approximately parallel to the v1 eigenspace, and then they'll bend and they'll come in tangent to the v2 eigenspace. So it's going to look like that. Okay, and so one thing you can see is that no matter where you begin, you're going to get sucked in to the origin. Okay, so in this case, we say that the origin is we say it's a node, and we say that it's stable. And the reason why it's and the meaning of stable means that if we start from some point that's kind of nearby, like out here, we get sucked back in to that equilibrium. No matter where you are, you get sucked back into it. And so we say it's stable. We might also say that it is a sink because things are getting sucked into it. And we might also say that it is attracting because things are getting sucked into it. So those are the various adjectives we would use to describe this kind of a situation. If you had, let's see, so if we looked at the case for when lambda 1 is greater than lambda 2 is greater than 0, then you're going to find something that looks very similar, except all the arrows are reversed. So now in this situation, let's see, so what do we got? Now what's going to happen is for large values of t, that's going to be when the v1 dominates, and that's going to be as these things are heading outward. So the entire conversation I said before is just sort of flipped around. So in this case, we would also say that if you start out here at any point at like this purple point, you're going to get spat out off into the distance. And this includes the fact, excuse me, this includes initial points that are arbitrarily close to the origin. They're going to go zipping outward on some trajectory, and they will go away from the origin. So as a consequence, we see this one is also considered a node, but we would say that it is an unstable node because small perturbations cause if you start at the origin, you will stay at the origin forever. But if you ever wobble off it, like if you start just infinitesimally close, boom, you'll take off and head away. So it's unstable. So we also refer to this as a source, and people might say this is repelling. Okay, now what if we have something where we've got lambda 2 less than 0 less than lambda 1? Okay, so now this one is a little bit different. So let's see, I'm going to do my axes. So there's x, there's y. And then, yeah, let's take the same sort of eigenvectors. So we'll take something here like this one as our v1, and something, those look sort of orthogonal, which maybe is misleading. Here, let's do, doesn't have to be perpendicular. We'll do some like screwball one. There we go. Okay, that satisfies my artistic preference. Okay, and so here's our v2. All right, so now let's see what happens if we pick some random point. So if we have something that is out here, say, then what's going to happen for negative values of t is that this one is going to be dominating, and this one's going to be sort of subsidiary or ignored. And so we're going to be following mostly along parallel to the direction of v2. So we might start off going something like this. Now, as we get to around t equals 0, then it switches over so that the other one becomes more important, and we end up getting sucked along with v1. Because remember, right now we're looking at this is a positive eigenvector for v1. So if you start a point here, it's going to scale big like that. Whereas if you start here, v2 has a negative eigenvector, so it's going to get scrunched in toward the origin. Again, I'm looking at e to the lambda t times v, right? And so this behavior persists all the way around. So the kind of curves that you're going to get are going to be like this. If I start over here, it'll get contracted toward the origin, right? So I have things that go like this and like this. So we get all these sort of hyperbolic shaped trajectories. Point started on this axis will head that way. So the sort of the currents of the streams go like that. Anyway, so that's the kind of thing that we have. If you are stuck at the origin, you're stuck there forever. But if you wobble off even the slightest bit, you're going to head away one way or the other. And if you get and you're going to get sucked towards the V1 eigenspace, or the lambda 1 eigenspace. And so we would say that this one is stable or attracting, so a stable submanifold if you want to get fancy, and this one is unstable. Because if you start even the slightest bit off of the E lambda 2 eigenspace, then so you start real close to it, but then you're going to get like sucked out and away eventually, and then you're gone forever. So this type of situation is, as you might guess, called a saddle point, and it's considered an unstable equilibrium.